Hermann Minkowski wanted to make geometry out of the physics of relativity. And in doing that, the basis of all that he was thinking about came in making time the fourth axis in a four-dimensional continuum of space-time. Since we can't draw four dimensions, let's follow Minkowski in starting with just two axes, a t-axis and an x-axis. Now in this system, we have to choose units. We could choose x divided into, say, miles and t in seconds, but that would be horribly inconvenient, because if we were trying to draw the trajectory of light, for instance, we'd have to go out 186,000 units of x before we went up 1 unit of time. So the light line would be almost indistinguishable from the x-axis. It would be so flat that we couldn't even see its departure from the x-axis. Better units? Choose light seconds for distance. How far does light get in 1 second? Like, you know, the idea of a light year is how far light gets in a year. Well, this is the analog for just a second. Well, in these units, things work out geometrically much more conveniently, because light travels 1 light second in 1 second, 2 light seconds in 2 seconds, 3 light seconds in 3 seconds, and so light travels along a 45-degree angle, very convenient for everything we're going to be doing. Now imagine that we're trying to coordinate clocks in the usual way. If we had set out two helpers equally spaced from me, and I wanted to have them both flash a light, and I got their signals at the same moment in front of my nose, I would conclude inevitably that those two flashes started at the same moment, that they were simultaneous, because they started from equidistant points and arrived at my nose at the same moment. Now, imagine that a train's moving with a speed v, and this train's got a ruler painted on it from the caboose at 0 up towards the front of the train, and we call the world line of the ruler's origin point the t' axis. That is to say, all of the moving ruler, the x' ruler, we'll call it, all of the x' equals 0 points in space-time, that is to say, the trajectory of the 0 point of the moving train, is just the t' axis. This idea of the axis is familiar to you, because if you have an xy graph in the usual way, the x-axis are just all the points where y is 0, and the y-axis are all the points where x is 0. So the t' axis is just all the points where the 0 point of x' goes along. Let's draw now the back, the middle, and the front of a moving train. So here you see on the graph, they're nicely parallel. Why are they parallel? Well, they'd better be, because if the back of the train actually met the front of the train, that would mean the train had been squished to a point. And if the back of the train separated from the front of the train, well, that would be very bad too. That would be a decoupling of the train into parts. So we can ask, if two events are simultaneous in the rest frame, are they simultaneous in the moving frame? Well, let's draw a space-time diagram and find out. Well, we've chosen our moving train such that it's moving along from left to right, such that you see that A, the flash A, occurs opposite the caboose driver's nose, and she says, definitely occurred right here in the caboose. And the front engineer going along says, I definitely saw flash B in front of my nose. So the flashes were separated equally from the middle of the train, no doubt about that. But the flash from B gets to the middleman in the moving train at point C, whereas the middleman of the train only gets the flash from the caboose driver at point D. So the train concludes, as night follows day, that flash B must have occurred before flash A. Why? Because B and A are separated spatially equally from the middleman of the train, but the flash B got to the middle sooner than the flash from the caboose. So there's nothing for it but to say that A and B were not simultaneous for the train. In fact, B occurred before A. Two events, A and B, simultaneous in the rest frame, are not simultaneous for the moving train.